Can spinning a superconductor twist spacetime? The strange possibility behind the study of gravitomagnetism in rotating superconductors, where some experiments suggest that rotating superconductors might produce gravitational-like anomalies, effects that classical physics cannot fully explain. According to general relativity, just like moving charges create magnetic fields, moving masses should generate gravitomagnetic fields. These are usually so weak that we only observe them around massive celestial bodies like Earth, e.g., in the Laglos or Gravity Probe B experiments. But intriguingly, some laboratory experiments claim to detect unexpected forces or field distortions from rapidly spinning superconducting disks. How could this happen, and is it real? In theory, superconductors expel magnetic fields through the Meissner effect and maintain coherent quantum states across many particles. Some researchers hypothesize that these quantum states, when rotated, may interact with gravity in unusual ways, amplifying gravitomagnetic effects. Example, in controversial experiments by Eugene Podkletnov, a spinning superconductor reportedly reduced the weight of objects above it, though these results remain unreplicated and highly debated. Analogy, it is like spinning a record player so fast that it subtly alters the floor beneath it, not by friction, but by bending space itself. While still on the fringe, these investigations challenge us to ask, could superconductivity provide a portal into new gravitational physics? Or are we chasing experimental ghosts? How can spinning superconductors whose macroscopic quantum state produces the well-known London moment in electromagnetism also generate measurable gravitomagnetic fields, seemingly amplifying frame-dragging effects far beyond the predictions of general relativity and standard superconductivity theory? In general relativity, any rotating mass drags space-time around it, creating an almost vanishingly small lens-thirring effect. Yet experiments with cryogenically spun superconducting rings have reported anomalous signals that suggest a gravitomagnetic field thousands of times stronger than expected. So far, so good, until we scrutinize the experimental and theoretical foundations. In pioneering work, Tajmar et al. Observed unexplained accelerations in laser gyroscopes placed near rapidly rotating niobium rings cooled below their superconducting transition. These signals disappeared above the critical temperature or when the rings were non-superconducting, implying a link between Cooper pair condensation and enhanced gravitomagnetism. If true, this would demand a profound revision of both gravitation and quantum field theory. At its core, the proposed mechanism hinges on the quantum coherence of the superconducting state. In a superconductor, electrons form Cooper pairs that occupy a single quantum wave function, described by an off-diagonal long-range order. Some theories suggest that this coherent state couples to the gravitational field via the principle of equivalence, effectively converting the superfluid mass current into a source of gravitomagnetic field far stronger than classical mass flow. Models invoking a gravitational London moment draw analogies between electromagnetic vector potentials and the metric potentials of weak field gravity. Yet even this mechanistic picture conceals deeper complexities. Independent replication attempts have yielded conflicting results. Some groups report null measurements or signals attributable to electromagnetic crosstalk, vibrational noise, or thermal drifting of sensors. The extraordinary amplification factor, up to 20 orders of magnitude above the classical lens-thirring estimate, remains unexplained, raising questions about experimental artifacts versus genuine new physics. Moreover, any gravito-quantum coupling must respect energy conservation and gauge invariance. Yet most models lack a fully consistent Lagrangian framework to embed a superconducting graviton mass term or torsion field. At even finer scales, quantum and material subtleties emerge. The interplay between the superconducting gap, vortex dynamics in type II materials, and pinning sites could modulate any weak gravitational coupling, making the effect highly sensitive to microscopic defects, rotation speed, and magnetic flux quantization. Some proposals extend to dark Virgio vacuum fluctuation-mediated forces, suggesting that Cooper pair condensation modifies local vacuum energy density and thus the metric tensor. These ideas link gravitomagnetic anomalies to speculative extensions of Einstein-Cartan theory or emergent gravity scenarios. In essence, the gravitomagnetism in rotating superconductors paradox challenges our most trusted frameworks, sitting at the crossroads of general relativity, quantum mechanics, and condensed matter physics. While tantalizing hints of anomalous effects persist, they demand more rigorous, repeatable experiments and deeper theoretical models. Whether these signals herald a new coupling between quantum condensates and spacetime or simply expose the limits of measurement, they underscore the ongoing quest to unite gravity with the quantum world. Gravitomagnetism is the weak field approximation of general relativity in which moving masses generate magnetic-like fields that can drag nearby inertial frames. In rotating superconductors, the macroscopic quantum state of Cooper pairs might couple differently to such gravitomagnetic fields compared to normal matter. This raises the question of whether the coherent frictionless electron pairs in a superconductor can amplify or detect frame-dragging effects far beyond classical predictions. If true, spinning superconductors could serve both as sensitive probes of gravitomagnetism and as potential sources of localized gravitational anomalies. Classical frame dragging by Earth's rotation has been measured by the Gravity Probe B satellite, but the effect is extremely small, milliarcseconds per year. It is like wondering if a perfectly smooth ice rink superconductor could slip more easily under a rotating platform than a rough wooden floor, normal conductor. Frame dragging arises from mass currents in general relativity, analogous to how electric currents generate magnetic fields in electromagnetism. In a superconductor, a circulating supercurrent carries mass via Cooper pairs, suggesting the generation of a gravitomagnetic field. Classical tests assume normal conducting currents, so substituting superconductive currents could in principle alter the strength or configuration of the induced frame dragging. This distinction underlies proposals that superconductors might produce measurable gravitomagnetic anomalies absent in standard materials. In lab-based rotating rings of normal metal, gravitomagnetic fields are far too small to detect, but superconductors may concentrate the effect. It is like comparing the airflow generated by a ceiling fan with wooden blades versus carbon fiber blades. The same rotation, but different material properties yield different air. The London moment describes how a rotating superconductor develops a magnetic field proportional to its angular velocity, reflecting a macroscopic quantum effect. By analogy, a gravitomagnetic London moment has been hypothesized. A rotating superconductor might generate a gravitomagnetic field tied to the Cooper pair condensate. Microscopically, the coherent wave function of Cooper pairs imposes strict phase relationships that could couple to spacetime curvature more strongly than incoherent electrons. This quantum coherence may enable superconductors to manifest enhanced gravitomagnetic fields inaccessible to classical matter. Rotating superconducting disks have been observed to produce minute magnetic fields even without external magnets. Consistent with the London moment, it is like a synchronized dance troupe moving in perfect unison that creates a more powerful wave of motion than the same dancers moving independently. Extensions of the Ginzburg-Landau theory incorporate gravitational potentials alongside electromagnetic ones, predicting coupling terms between superconducting order parameters and spacetime curvature. These coupling terms can modify the supercurrent distribution under rotation, theoretically yielding anomalous gravitomagnetic fields. The key mechanism involves non-minimal coupling of Cooper pairs' effective mass current to the spacetime metric tensor. If these theoretical predictions hold, rotating superconductors would generate gravitomagnetic fields exceeding classical estimates by several orders of magnitude. Calculations based on modified Ginzburg-Landau equations suggest a gravitomagnetic field proportional to the superconducting carrier density and angular velocity. It is like adding an extra spring to a pendulum system so that it oscillates with a frequency entirely different from the simple pendulum prediction. Quantum coherence in superconductors leads to superfluidity of Cooper pairs, eliminating viscous drag and preserving quantum phase over macroscopic distances. This superfluid mass current can maintain a persistent rotation with minimal energy loss, potentially sustaining gravitomagnetic fields indefinitely. The superfluid analogy suggests that superconducting rings could act like frictionless flywheels, exchanging momentum directly with the vacuum. Their ability to preserve ordered motion makes them prime candidates for amplifying any gravitomagnetic coupling. Superconducting quantum interference devices, SQUIDs, detect minuscule magnetic flux changes by leveraging coherent electron pairing over microns. It is like a perfectly balanced flywheel that, once spun, continues to rotate smoothly, pushing against any coupling force longer than an ordinary spinning top. Several experimental groups, notably Podkletnov and later Tajmar, have reported small anomalous weight changes or accelerations near spinning superconductors, effects that appear only past specific angular velocity thresholds. These observations suggest a nonlinear onset, where below a critical rotation rate no anomaly appears, but above it a measurable force emerges. The threshold nature implies cooperative quantum effects that switch on once sufficient supercurrent density is reached. However, reproducibility has been poor, and the anomalies remain controversial. Tajmar's experiments indicated accelerometer readings of 10 to the power of 98 G near a niobium superconductor spinning above 5,000 RPM, but follow-up tests yielded conflicting results. It is like hearing a faint whistle from a speeding bicycle wheel only when it surpasses a certain RPM, and then not hearing it on a repeat ride under the same conditions. If confirmed, enhanced gravitomagnetic fields from rotating superconductors could revolutionize inertial navigation and gravitational wave detection by providing compact, high-sensitivity sensors. In propulsion, reactionless thrust based on gravitomagnetic coupling might enable spacecraft to accelerate without propellant, drastically reducing mission mass. Such technologies would redefine paradigms in astrophysics, geodesy, and space exploration. The potential applications underscore the high stakes of resolving this paradox. A gravitomagnetic thrust device could continuously accelerate a satellite at micro-G levels, achieving interplanetary velocities over months without fuel. It is like discovering a hidden current in the ocean you can surf indefinitely, rather than relying on finite coal reserves for a steamship. Detecting gravitomagnetic anomalies at the lab scale requires sub-nanoradium precision in gyroscopes or accelerometers, rigorous thermal isolation and elimination of electromagnetic crosstalk. Theoretical models must reconcile any observed effects with conservation laws and general relativity, avoiding violations of energy momentum conservation. Many reported anomalies could stem from thermal gradients, vibrational noise, or electromagnetic interference. Both theory and experiment face the daunting task of distinguishing genuine gravitomagnetic signals from mundane artifacts. Replication attempts at well-shielded cryogenic facilities have failed to reproduce Podkletnov's weight loss claims, suggesting environmental factors at play. It is like trying to detect a whisper in a hurricane. Without perfect wind shielding and background noise control, the test is inconclusive. Advances in quantum sensors such as atom interferometers and superconducting gravimeters may achieve the sensitivity required to confirm or refute gravitomagnetic engine theories definitively. Theoretical work on quantum gravity and unified field models could clarify how superconductive coherence couples to spacetime. Collaborative open access experiments with standardized protocols will be crucial to resolving reproducibility issues. Whether or not spinning superconductors yield gravitational anomalies, the pursuit unites quantum theory, superconductivity, and gravitation, potentially illuminating new physics at their intersection. Planned experiments using space-based superconducting gyroscopes aim to isolate gravitomagnetic effects in microgravity and ultra-low noise conditions. It is like launching an observatory into orbit to escape atmospheric distortion for a clear view of faint cosmic signals.